Hello everyone, this is chapter 10.2 where we'll be discussing operations with matrices. And first I want to get the notation down a little bit just so it's easier to talk about what the operations do for us. So we're going to let A be Aij in brackets, where B is Bij in brackets, and they are m by n matrices. So basically what this means is that the general notation for a entry in A is Aij, where I is the row and J is the column that this entry is in. So we actually saw how to expand that out in 10.1 kind of. I at least showed you the generalization of how you expand it out. This notation is just a little more compact, if you will. Now, the notation isn't super important as much as what these operations say to do. So in practice with examples, we'll actually see what this really means. So anyways, these are the notations for the general m by n matrices. And matrix addition is defined to be as follows. So if you have two matrices of the same dimension, m by n, in this case they're both m by n, A plus B is just the matrix whose entries are the Ij entry of A added to the Ij entry of B, meaning we are to add term by term. So there's two things I should say here that are of particular interest, and that is only matrices of the same dimension can be added. Same dimension can be added. If they have different dimensions, then their sum is, well, non-existent. Their sum is undefined. The next thing I should say is that this definition here really says to add entry by entry. So add each entry of one matrix to the corresponding entry in the other matrix. And we'll see that in practice with this example. The next thing is scalar multiplication. So if C is just some real number, and we want to multiply to the matrix A, remember A isn't, well, it's a matrix, so it's not a number, it's like it's an array of numbers, it's a set of numbers kind of. So what we're going to do is we're going to multiply this number to that matrix. And how we do that is we just basically, well, what this says, we multiply that number to each entry of the matrix. So think of like distribution. In fact, I very often think of this as like a scatter shot. But the best way to think of it, I think, is distribution. So very often people think that the scalar distributes to each entry in the matrix. Distributes to each entry. And here, of course, the word scalar is just a name for a number itself, a single dimension number. A matrix we're kind of treating as a number, but it has multiple numbers as a part of that one object, I guess you can say, multiple components to it. So here A and B for this example are given to be these, so we're treating A as one thing, B as another thing. And we want to find this, we want to find 2A minus 1/2 B. So in fact, in doing this, there's actually a few things we're asked to do, which I think this is a pretty full example in the sense that I'm handling both of these at once. So let's kind of consider piece by piece here. So 2A, I think I have some room to write it here. A is 3, 0, 2, negative 1. So how do you multiply that matrix by 2? Well, according to scalar multiplication, you multiply 2 to each of these. So notice 2 distributes, and you kind of see why I call it a scatter shot, because it kind of scatters to each of them, multiplication-wise. So our result here is 2 times 3, 2 times 0, 2 times 2, and 2 times negative 1. And this right here is 2A. Perfect. But now we need negative 1/2 B. So let me just do that over here. Negative 1/2 B, well, B is 2, negative 5, negative 4, negative 2. So we need to multiply each of them by negative 1/2. So notice these three are even, so we can just divide by 2. And since it's negative, we need to change their signs as well. So now this becomes negative 1, positive 2, positive 1. Good. And then negative 5 times negative 1/2 is positive 5/2. And that's all we really have there. But now, notice this is negative 1/2 B and this was 2A. But we want to add them together. So in reality, I just don't have space to write it out in a nice way. And it's kind of all over the place. But in reality, we're taking this result and adding it to that result. So let's just write it like that. So the first result was 6, 0, 4, negative 2. And the second result that we're adding this to is -1, 5/2, 2, and 1. So far all we've done is scalar multiplication. Now we have to use matrix addition. And again, the thing to keep in mind is that they have to have the same dimensions. They're both 2 by 2, so we're good. And we add entry by entry. So the first row, first column, look at those entries, 6 and -1, add those together, we get 5. Perfect. And now, first row, second column, 0 plus 5/2 is still 5/2. Great. Second row, first column, 4 plus 2 will be 6. Second row, second column finally is -2 plus 1 is -1. And that's our answer for this example. Awesome. So now we're going to take a look at something a little different. In fact, one thing that you may be asking yourself is well, can we multiply two matrices together? And the answer is yes, we can. But we'll do that in a little bit. For right now, I want to talk a little more about this, and we're going to discuss some properties that unfold based on our definitions of scalar multiplication and addition. So let's take a look at those properties right now. All right, so here are the properties I was just referring to. So these properties, of course, involve matrix addition and scalar multiplication. So here we let A, B, and C be some matrices of the same dimension, and C and D be scalars. And these are true. And in fact, they're true based on the definitions. And it's not hard to verify these, in fact. I'll name a few. I don't know if I'm going to name all of them, but let's see. So this is, of course, a commutativity. Commutativity of addition. This is associativity of addition. This would be associativity of scalar multiplication. This would be the identity, the multiplicative identity, but it's a scalar multiplicative identity. So 1 times anything is itself. But notice this is the number 1. And of course, if you scale 1 into each entry of a matrix, you get back the same matrix. So there's some explanation of a few of these that are kind of obvious right off the bat. And you can just kind of see by trying to give yourself some examples to see if you can figure out why these are true. Here, this is distribution over a scalar multiplication. And there's actually 2 ways you can distribute. And in fact, this is distributing one scalar across 2 matrices being added. But here, this is distributing one matrix over 2 scalars being added. So that ends up being the same thing. So this is also distribution. So these properties hold basically because of the properties that these correspond to with normal numbers, kind of how we're used to, with just real numbers, basically. And it's really because the definition of matrix addition and scalar multiplication are pretty straightforward in the sense that they're basically just borrowed from how we're used to things behaving with just regular numbers. So it's something you can think about a little bit if you want, but to be quite honest, we won't really be seeing too many examples involving these. I gave 1 here, but that's really as far as I'm going to go. And here, of course, we can distribute 3 amongst each of these. So here's what I'm going to do. I'm going to do this kind of fast. So I'm going to distribute 3 into the first one, so it's 906. Want to leave a little bit of space. There we go, 906 on top. 3, -3, 9 on the bottom. 3, -3, 9. And then plus, distributing 3 into this one now, will give -3, 6, 9. -3, 6, 9 on top. And then for the bottom row, we have 3 times each of these, which is 12, 15, -6. 12, 15, and -6. And now adding entry by entry, we of course get, let me write it above here, we get 6, 6, 6 plus 9 is 15. Let's see, that's going to be 3 plus 12 is 15. -3 plus 15 is 12. And then 9 plus -6 is 3. And something to notice is, of course, this is the exact same result we would have gotten if we added these together first and then multiply that result by 3. And you can clearly see if you divide each of these by 3, you get 2, 2, 5, 5, 4, 1. And in fact, if you add these, you get 2, 2, 5, 5, 4, 1. Nice. So we see at least some of these properties happening here. But again, that's really all I'm going to say here. Now we'll move on to matrix multiplication. and see really what that's all about and how it's defined, because it's not as straightforward as you might imagine. Alright, so finally, here's matrix multiplication. So we're going to let A be this matrix Aij, where it's an m by p matrix. We're going to let B be Bij, where it's a p by n matrix, so they're not the same dimension. But notice the column dimension of the first is equal to the row dimension of the second, so keep that in mind. Then A times B in that order, so A times B in that specific order, is the matrix whose entries are Cij, where each entry is this, the sum of products of entries in A times entries in B. So in particular, notice that these inside dimensions are the same. So Aij, remember what Aij is, that's the ith row, but the first column entry. B1j is the first column, but the the first row, but the jth column. So that's kind of something to keep in mind. And in fact, really what's going on here is what we're doing is we have these two matrices we're multiplying together. And what we want to do is we want to pick the rows from one, the columns from the other, and we're multiplying them in a specific way where we end up with a new entry for that row and that column. So to be honest, you can go through this and try to label things and figure it out based on this. But really the best way of doing it in practice is just by visualization. So one thing that may help before we get to the actual visualization I want to show you is that remember, every matrix, the dimension of any matrix is row by column. We know that. So if we go with that and keep that in mind, we'll consider this our row matrix and consider this our column matrix. So now, it's going to be a little hard for me to show you, but I think we can do it. So now if we highlight the first row and highlight the first column, and we multiply these pieces entry by entry, so 3 times 5 plus 0 times 2, that will give us the first row, first column result, or I guess entry, for the resulting multiplication. So this is going to be 5 times 3 plus 2 times 0. And really what we're doing here is exactly what this is telling us to do. By the way, before we move on and continue with this process, I must say that notice this is an m by p, this is a p by n, and in doing this process for each of them, with this multiplication, our resulting matrix will actually be an m by n matrix. So you can tell when two matrices are compatible multiplication-wise if let me kind of show you here. So this is a 2 by 2, this is a 2 by 2. If these two are the same, in other words, the column entry of the column dimension of one, the first one, and the row dimension of the second one, if they're the same, then that means that you can line things up perfectly like this. Otherwise, if this one's too large, you can't line things up and there's overlap, or if this one's too large, the same thing happens. So they must be such that these dimensions are the same. These two we don't care about, they could be different. And in fact, the result will just be this dimension by this dimension. Notice here, m by p and p by n, if you cancel the p's, you end up with an m by n. So that's really the visualization of what's going on as far as compatibility goes. But let's continue and move on with this idea here. So now we're done with the first row, first column entry. And now if we move down to the second row, but still with the first column, this will give us the second row, first column entry of our resulting multiplication. So that's going to be 5 times 2 plus 2 times negative 1. So we're done with the first column. And now now let's move on to the second column. So now we're finished highlighting the first column. Now we'll highlight the second column, and I'll do the first row first. So first row, second column. We know how to gather things and multiply them together, just again, entry by entry. So first to first, second to second, basically. And we'll get, let's see, that's going to be negative 1 times 3 plus negative 4 times 0. Good, I think we have space, yep. And then now we're done with the first row, first column, or first row, second column, I should say. And now we're on to the second row, second column. And now if we multiply these in that way, well, let's see, we get negative 1 times 2 and negative 4 times negative 1. So plus negative 4 times negative 1. Now just combine and then we'll get our answer. So here, this is going to be 15 plus 0, which is 15. Below it's 10 minus 2, which is 8. This is negative 3 plus 0, so that's negative 3. This is negative 2 plus 4, and that's positive 2. So this is the answer of that multiplication. Now, funny enough, matrix multiplication is not commutative. And you can see that right away because even though here we have an example where they're both square matrices, meaning that they're both the same dimension for column and row, so 2 by 2, a 3 by 3 is another example of a square matrix. But they're both squares, so they're compatible either way, that's fine. But that doesn't necessarily mean the results are the same. In fact, the result won't be the same. And if you want to verify that on your own, I'll let you verify that on your own, of course. But let me just say that if you multiply two matrices in either order, chances are they will not give you the same result. There are some rare instances where that happens, and we'll see one in a little bit. But you can also tell that specifically if you don't have square matrices, let's say it's a 3 by 2 and a 2 by 4 or something like that. Those are compatible by multiplication because those dimensions are the same. It's 4 by 2 and 2 by 4, or 3 by 2 and 2 by 4. But notice if we reverse it, it would be 2 by 4 multiplied by a 3 by 2, and 4 and 3 don't match, so they're not compatible that way. Meaning that if you switch the order of multiplication, you can get entirely different results. Notice what I just said, even though I'm not writing it down. One way it's doable, the other way it doesn't even exist. Or here they'll both be 2 by 2 results, but if you try it, you'll see that you'll indeed get something entirely different. So it's kind of interesting to think about. And again, I said I'll show you a different visualization of how to come up with this idea. In fact, I have a different way of thinking of it, but I'm going to cook up another example right now. So I'm going to erase this. I'll show you a little more of an extravagant example, and then I'll introduce some kind of newer concept that has to do still with matrix multiplication, though, where we'll see an example where switching the order will actually give you the same result. Right, so here I have some less simple examples where the dimensions are a little different. So let's first label the dimensions here to make sure we can even actually multiply these things. So notice this has 3 rows and 2 columns, so this is a 3 by 2 matrix. We're multiplying it to a 2 by 2 matrix. These dimensions, inner dimensions, are indeed the same. And if you cancel them out, it tells us our result will indeed be a 3 by 2. So expect to get a 3 by 2 as your answer. Good. Here, this is a 3 by 1, and this is a 1 by 3. Now, funny enough, here if you look at the original, first example here, if you switch the order, they're not compatible, because then you'd have 2 and 3, and those aren't the same. But here, if you switch the order, funny enough, they actually are the same. Well, yeah, the inner dimensions are the same anyways, so you can actually do that. In fact, we'll do that afterwards. But for right now, I'm going to try to give you a different way of visualizing how you multiply two matrices. Because you could do the whole row column thing, that always works, but I have a better way of doing it. At least in my mind, it's a better way of doing it. And really what I want to do is I want to grab all columns on the right matrix, swing them over as rows above this matrix one at a time. So first I'm going to do the first column, swing it over, then multiply down, add across. So I'm not going to write too much of the details, but let's just see what we get. So when we multiply the red numbers down to the black numbers, multiply them down, add across, you get, let's see, for the first row, I get 6 plus 4, so that's 10. Here I get negative 9 plus 2, that's negative 7. And then for the third one, I get 9 plus 10, which is 19. So I hope we see how I'm doing that. I'm just grabbing the red numbers, multiplying it to the black numbers, adding those together one at a time. So here I get 6, 4, add those, you get 10. Here, these two to these two, I get negative 9 and 2, add those, you get negative 7. And then these red to these two black, we get 9 and 10, those add to 19. Great. So now that we've done the swinging over of the first column, that one's done. Now we're going to swing over the next one to get the second column. Because this is the first column of our result, now we're going to get the second column of our result. So So this is going to be 5 times 2 is 10, 6 times 2 is 12. Add those, you get 22. Good. And then negative 15 plus 6 is negative 9. And then 15 plus 30 is 45. So that's what I'm getting there. And if you want to try and compare it to the other way I showed you previously, you can. It's the same exact thing. And you can see that it's the same exact thing because really all we're doing is we're multiplying each row to each column in that way. But when you swing it over, it's easier to pair them up. So that's why I think this is more visual, and in my eyes it's easier, but of course everyone sees things differently, so it kind of depends. But at least I'm giving you that perspective. And now this, well, okay, so we can definitely do this. And notice our result here will be indeed a 3 by 3. So these cancel, we get 3 by 3. So keep that in mind. But notice really what's going on is if you swing each of these over one at a time, it's just a single number. So really we're multiplying this column by 5, then by 1, then by negative 1, and we'll get these 3 different columns. So each of them times 5 is 15, 10, 5. Each of them then times 1, if you swing over 1, which sounds funny because we're not really swinging it over, it's just a single number really. We get 3, 2, 1. And then I'm not going to write the next one, but you can kind of see that when you swing the next one over, you get negative 1 times these will give you those numbers, but negative. And there we go. We indeed get a 3 by 3 result. And like I said, I wanted to show you the other way around, just to show you that we obviously get something different. So just to show you, I think we have space here as a third example. We're going to do the same matrices, but multiplied in the opposite order. So 5, negative 1, multiplied by 3, 2, 1, like that. Let me make sure it shows on the screen. Good. So now notice, if we, let me get rid of this labeling here. I guess I can increase it a little bit. Just lift it up like that. Okay. So notice, of course, this is a 1 by 3, this is a 3 by 1. The 3's will cancel, and you'll be left with a 1 by 1 matrix, which we haven't really seen yet, but really it's just a number inside of brackets. So if we swing this column over on top of these, multiply down and add across, we get 15 plus 2 minus 1. 15 plus 2 is 17, minus 1 is 16. So the number we get inside those brackets are 16. So this is our 1 by 1 result of doing that. And notice clearly, like I said earlier, multiplying these in different orders gives you completely different results. And now we're going to take a look at a different kind of idea, but it's still within the realm of matrix multiplication, where we actually do get the same thing multiplying. It's kind of a trivial case, but we'll take a look at that right now because we need to see it before moving on to 10.3. Right, so now I've written some properties of matrix multiplication here. I'm not going to talk about them too much, but I'll just say a little bit here. So let A, B, and C be matrices of the appropriate dimension in order for the multiplication to even exist. And let C be a scalar. So we have associativity of multiplication for the first property. 2 and 3 are both distribution over matrix addition. But notice matrix multiplication is very order specific. So here there's distribution from the left, where this is a matrix multiplying over addition on the right. So distribution on the left versus distribution on the right. And here this is associativity between scalar multiplication and matrix multiplication. And in fact, it's not really just associativity, it's more like associativity combined with I guess you can say, commutativity in some sense, because you can scale C to A or you can scale C to B first. So that's something to think about. And I'll let you work these out on your own if you like. I'm not going to give you a particular example of this. Instead, I think I'll move on to a different idea, which I think is a little more important in my opinion, and that's multiplicative identities. So the multiplicative identity, the notation is I sub n, will be this n by n matrix. And I know it's a lot to look at, but really it's the matrix, square matrix, whose entries are all 0 except for the main diagonal going from the upper left to the lower right. So they're all 1s in that diagonal. And, well, just to give you some examples, I2 is 1, 0, 0, 1, kind of like we see in the example listed below. And I3, for instance, is 1, 0, 0, 0, 1, 0, 0, 0, 1. And this shape should look pretty familiar to us. if you remember what we saw back in 2.1, just the previous video, 10.1, the previous video, this is really what came from reduced row echelon form. So there's some parallels there, I guess you can say. Something I want to say with the multiplicative identity is that it kind of mimics what 1 does in multiplication with real numbers. So 1 multiplied by any number in any order will give you back the same number. And the same is true with these multiplicative identities. So if you have a matrix A and you multiply it to the matrix I, assuming they're compatible, this will always be equal to A, even if A is non-square. So for example, if A is a 3 by 2, then multiplying in this order, you better use I2, but then that'll still give you back the same 3 by 2. And you can try those kind of weird examples if you like on your own again, but I'll give you an idea of why it works here for 2 by 2s only. So again, remember how we multiply. We're going to swing these columns over, so 0, 1, multiply down, add across, but notice, since we have a 0 on top of here, that whole column becomes 0, so when adding together, we really just get a repeat of the original first column. Funny. Similarly, when you swing this one over, 0, 1, the same thing happens, but now to the opposite column. The first column becomes all zeros, so we're just adding that to, the second column. So we get actually a repeat of the second column. In other words, we get that same matrix back. So it acts just like how 1 acts with numbers. 1 times any number is the same number. So here it's I times any matrix is the same matrix. And in any order. So, like I said, matrix multiplication is not commutative in general, but there are some instances where it is commutative. The identity is one instance of that. So here, if you multiply them in the opposite way, you'll still get the same result. So let's see that here. If we swing 3, 2 over, notice what this does is, well, for the first row, we get 3 plus 0, and for the second one, we get 0 plus 2, meaning, well, we get 3 on top and 2 below. Great. And now for the second one being swung over, negative 3, 1, it's the exact same thing. We get negative 3 on top only because negative 3 times 1 plus 0 is negative 3. And for the second row, second column, we get 0 times negative 3 is 0, plus 1 times 1 is going to be 1. So notice again, we get back the same matrix. All right, so again, that's all I wanted to say for 10.2. And so in 10.3, we're going to be taking a look at an extension of what we saw here. So notice, basically, we looked at operations involving matrices as far as addition, subtraction, multiplication. We didn't see division, though. And in fact, you can kind of divide. You basically have to multiply by what is called the multiplicative inverse of a matrix. And we'll take a look at that actually in 10.3. Notice that we kind of subtracted in this section as well, but notice subtracting is the same as adding to the negative of a matrix, and a negative of a matrix is just scaling in a negative 1 as a scalar. So kind of think of that when we so-called divide, we're just multiplying by the multiplicative inverse of the second matrix in this case. Anyways, we'll see that in the next video. Thanks for watching. Hope you enjoyed this one. I'll see you in the next video.